positives started far apart, you remember the potential was low, because now they're only going to go like that, just a little bit further apart. So we talked about potential previous to this. Well, if you talk about current today, and you look it up in your reference table, the equation you're going to find is this one. I is current. I know you wish it was a C, but it's not. Sorry. Current is an I. Q, what was Q? What did Q stand for?
Charge.
Charge. The units that represent the guy's name for
Coulomb.
charge? Coulomb. Time is in seconds. So a Coulomb per second would be current. But nobody says that. You never hear anyone say, oh, I have 5 coulombs per second. It just doesn't, people don't say it that way because there's another unit that means the same thing, but it's also after someone's name. It's an amp. Mr. Ampere. Okay, so it's an amp. So when you talk about current, you talk about amps of current. Now just to make this real for you, if you have an outlet that you might have your phone charging over there, as that student does, plugged in, how many amps does that outlet, how many amps can that outlet possibly provide? What's the max that that outlet provides?
210.
You're thinking voltage. That's a different thing. And voltage, remember, is potential. If you're talking about the amperage, that outlet there would either be a 15 amp outlet or a 20 amp outlet. I can't really tell by just glancing at it from here, but you'd have to go in the back where the circuit breakers are. And it would either be set so it can handle 20 amps, that means a certain number, 20 coulombs per second, or it would be set for 15 coulombs per second. If it's set for 15 and you go to 16, you try to pull out 16, what's going to happen in the back room? What? No, it won't fry. What happens in your kitchen if you try to run too many devices on the same outlet?
The lights flicker.
And sometimes everything just turns off. That's the circuit breaker switching off as a safety. Because if you try to pull something like 18 amps out of a 15 amp circuit, you're trying to pull too many electrons through that wire gets hot, and when the wire gets hot, it can melt and burn your house down. So they have safety features, circuit breakers, and when you try to exceed the number, the thing kicks off. Alright, that's the basics of it. We'll learn that in more detail later, but that's the basics. Alright, so the next little thing I want to talk about is, so that's current, that's flow of electrons. Well, we've done this other topic, power, in the past, and back in last time we did it, it was work over time. This was a reference table equation. Alright. And it basically just said, all right, work was a force times a distance, and time, so it was how quickly you were doing work. And we ran up the stairs, and we calculated our power. Everyone with me on that? Remember all that? Well now, when we're talking about, electrical power, we're still going to start with this same equation. But now, work is no longer force times distance. We learned a couple days ago that there was an equation, we wrote it, I'm trying to think which form we wrote it. I think we wrote potential is work over charge. Isn't that the way we wrote it the other day? Is this ringing a bell? Mm-hmm. So if I rearrange that, it would be voltage or potential times charge. So that's how I'm going to plug it in. I'm going to say power is potential times charge over time. What do you see in that equation that we could probably simplify?
The current.
Q over T, well you guys are quick today. Q over T is the same as current. So we could say, this is another reference table equation, we could say that the power is simply how much potential you have, and potential is in what units again?
Volts.
Yeah. Remember, it's the potential to do work is volts. And I, which is current, which now is in these new units we just learned called amps. So we got power as being a volt times an amp. But no one says that. That's not what everybody says. What did we use before when we were talking about power? What unit did we use?
Joules.
That's work. One step further. Joules was work. Power was
Newtons.
coulombs. Coulombs is charge. Newtons is force. We're going through them all. We'll eventually get there. What is power? Hint, light bulbs. Watts. So, power is still going to be in watts. And now, the markings on a light bulb might make more sense to you, because if a light bulb says that it's a 100-watt light bulb, what it's saying is that if you took the voltage and times it by the current, it would have to come out to be 100 watts. That's how they're labeling the light bulbs. Now the newer light bulbs, the LEDs, are much more efficient. So it's a little confusing, because in your mind, you think of a 100-watt light bulb as being a really bright light bulb, right? But now you can buy a light bulb that is the same brightness as that 100-watt light bulb, but when you read the wattage, have you ever looked at those new packages? It might be like 17 watts. But it's the same brightness as a 100-watt light bulb. So you've grown up with this idea that 100-watt is like how bright it is, but 100-watt has nothing to do with how bright it is. 100-watt has to do with what? What is the 100-watt meaning? It's potential and current. It's how much electricity stuff, for lack of a better term, it's using. So now the new light bulbs use less of this, but produce the same amount of light, which is why they've switched over. Okay? Now, last thing before I cut this video off is, if you're going to be dealing with power, and you're going to be dealing with potential, and you're going to be dealing with current, you need devices that can measure these things. And if you are trying to measure potential, we'll start there. So we're trying to measure how much potential something has. What you're going to use is a voltmeter. Now voltmeters, I'm not going to try to draw a picture of what they look like. That doesn't matter right now. But if you have a circuit hooked up, and I'll draw you a quick one. This is a battery. This is a light bulb. This is a switch. And that's it. I just have a light bulb and a switch. And if I put the switch in the closed position, that means the light bulb is on. Makes sense, right? All pretty simple stuff. Well, if I want to use a voltmeter and I want to see how much voltage that light bulb is using, the way I have to hook it up is like this. I have to take that thing, this represents the voltmeter if you didn't get that. That thing represents the voltmeter, and I have to touch one side of it to one side of the light, and one side of it to the other side of the light, while the circuit's on. And what it'll tell me is it'll say, this light bulb is using this much potential, or this much voltage. Now, since I only have one light bulb, how do you think the light bulb potential is going to compare to the battery potential? If I, later on, I go and I check this right here. What do you think is going to be true about these two if there's only one light bulb in the circuit?
It's going to be the same.
It's going to be the same, because it's the only thing using electricity. If I start adding light bulbs, then each of the light bulbs is going to be a different number than the battery, because the battery is supplying all of the light bulbs their electricity, their voltage, their potential. Okay, so that is a voltmeter, and this way that we just hooked it up, where it's like separate, is called hooking in parallel. Parallel, that's an A, parallel hookups. Okay? So, the one other device we need is in order to measure current. So, we're measuring potential, we're measuring current. So if we want to measure current, we need what's called an ammeter. Don't be fooled, a lot of people think it's amp meter. It's not, it's ammeter. Ammeter. It's an ammeter, and I'll draw the exact same circuit. So you got a battery, you got yourself a light bulb, you got yourself a switch. We'll leave it in the closed position so the light bulb is on. Good, light bulb's working. This thing's all hooked up. Where do we put the ammeter? Just figure out. Now what's the ammeter reading again? Ammeter.
Measuring the
And current is a measure of what?
coulombs over time.
So it's the flow, it's the coulomb over time, so it's how many electrons go by. So basically, if you're thinking of an ammeter, you're thinking of a device that's counting electrons, 1, 2, 3, 4, 5, as they go by. Whereas if you're thinking of a voltmeter, you're thinking of a device that compares this side compared to this side. This side has this much potential, this side has this much potential. So this is comparing two potentials. This is counting electrons. That's important for you to understand. Well, how do you hook it up? If you're hooking up an ammeter, you actually have to disconnect something. Now don't change your picture on your paper. But you're going to disconnect one of these wires like that. I just disconnected that wire. I'm going to put the ammeter there, and then I'm going to get a new shorter wire to hook it into the ammeter, then hook to the other side of the ammeter and go back to where I disconnected. So on your picture, all you really got to do is draw an A right in the middle of the wire. But the way you actually did it physically in the lab was you'd have to disconnect one of the wires, put the ammeter in there, and then reconnect so that all the electricity has to go through this. All electricity goes through an ammeter. Okay? So it goes right through it. And when you do it that way, what you're doing is you're hooking it up in series. This is a series hookup. So for today, that's your lesson on power, ammeters and voltmeters, and current. That'll allow you to do the homework for today, physics.